Hi, everybody. Thanks for joining. I'm Kareen Wallach. I lead developer community at Startree. And today we have a very awesome presentation for you on advanced indexing, JSON and text by two of our very active Pinot contributors and committers, PPMCs, Jackie and Sid. So I'm going to give them a little bit of a formal introduction because I think it's well deserved. So since Jackie's going to go first, I'll introduce Jackie, and then once his session is done, we can do a little short Q&A, and then he can answer questions during that time. If you have questions while he's presenting, feel free to put them in the chat. We will have some other Pinot contributors inside the chat also, so they'll be able to also answer some questions. So don't hesitate to ask questions, but we will also be doing a Q&A at the end. So we're going to start off with Jackie's presentation. We'll do a short Q&A, and then we'll do an introduction for Sid. We'll have his presentation and then a short Q&A. Altogether, we're thinking it's probably going to last us about an hour. Maybe we'll go a little bit over, but that's probably what we're expecting. And we will be recording this session. It's also going to be available on YouTube, as you guys are probably watching it on YouTube now. So we can get started. I'm not going to hold you guys any longer with my blah, blah, blahs. So we're going to start off with Jackie. So Jackie is a founding engineer at Startree and a PPMC and committer for Apache Pinot. Jackie got his bachelor's degree from Tsinghua University and a master's degree from Carnegie Mellon University. And then he started his career at LinkedIn for 4 years, and then became a PPMC and one of the top contributors for Apache Pinot. Jackie's goal is to make Apache Pinot the fastest online analytics platform on the market. It's a really, really good goal. So I'll bring Jackie in now. And hi, Jackie.
Hi. Hi, Kareen. Can you hear me?
Yeah, I can hear you.
Yeah.
So I'm going to share your presentation, and then I'll jump off, and I'll see you back at the end of it for a Q&A.
Okay, sounds good.
All right.
Thanks, Kareen. Yeah. Okay, so good morning, everyone. So welcome to my talk. So today I'm going to talk about the Apache Pinot JSON index and the plug and play experience with it. So let's start with a use case. So since it's a meetup event, I'll use a meetup RSVP stream as an example. So let's see, right now I have this stream data source, and I'm trying to run some analytics with the following questions. So I want, like, for example, the number of online meetups. And then I want some analytics on all the meetup events from groups in Mountain View. Or also, I want to know about the meetups about open source project. So let's think about how to answer these queries. So let's first take a look at an example message. Actually, this example message is captured by Pinot, ingesting data from the RSVP stream. And actually, this event is when I subscribe to this meetup event. So as we can see here, we got several nested fields. One is venue and the member and also event. So in the venue member event, there's an ID field where, like, conceptually we can use it to join multiple tables. And then, yeah, of course, the event is this event, advanced indexing JSON and text. And then within the member, we can see the RSVP member is me, Jackie, as the member name. So actually, there's another interesting field called group. So group is slightly different with other nested field. It has another level of nested objects within it. And then let's take a look at the group topics. So actually, it's an array of nested objects inside. So let's think of this example message and think about how we can store it in Pinot. So there are two options. I'll start with the option without JSON support. So basically, we need to use the common Pinot way of storing it in a fixed schema. So let's see, like, for example, the venue and event field. So basically, if we want to store it with fixed schema, we can simply flatten it into something like, basically, we flatten the object into all these simple fields. For example, for venue, we can flatten it into four different columns: venue name, venue longitude, latitude, and ID. Similar for event. But let's take another look at this like more complex object group. So for the group topics, we will run into some challenge when trying to flatten it. So should we flatten it into a multi-value column? But then there's another level of nested objects within it. So for each group topic, there are URL key and topic name. So then the second option, can we flatten it to like this? This is like another level of flattening to the nested objects. We flatten it to group topics URL key 1 and topic name 1, URL key 2, topic name 2. So seems it works, but what if there are 100 group topics? I don't want to store like 200 columns. It's very inefficient. Then another option is probably we can store multiple tables. And then, yeah, that can solve this problem. Basically, we store a RSVP table along with another group topics table. And then probably we can run some join during the query time. So yeah, then again, so for example, the online meetups. So the online information is extracted from the venue field. So no problem to solve the online meetups question using a flattened RSVP table. Similar for the meetups from groups in Mountain View, because that is also a simple field. But the third question is become interesting. So the open source project is actually stored as the group topics. So we have to join this flattened RSVP table with the group topics table to get the answer for the third question. So in order to store these two tables, let's take a look at the architecture we need. So first of all, I have a meetup Kafka stream with the meetup JSON topic data inside. Then, so because I want to basically flatten it and then split the data into two tables, I need a Flink or ETL pipeline to denormalize and flatten the data into two Kafka topics. One is the RSVP topic. Another one is the groups topics topic. Then I need two Pinot tables to store these two tables. Okay, so then at query time, in order to answer the third question, basically I can use the Pinot lookup join feature. But if the table is more complicated and cannot be solved with Pinot lookup join, I need to leverage Presto to do the join and use Pinot as a data source. As we can see, like this architecture is quite complicated, and it requires multiple extra services like the ETL service and also Presto. Then let's take a look at the second option, the JSON support. Basically, here we can use flexible schema. So for JSON support, we can directly dump the JSON blobs into Pinot. So as we can see here, columns, I can store the flattened field called, so we have 4 nested fields. So we can store them as venue JSON, member JSON, event JSON, and group JSON. And then in the values, we can simply dump the JSON into a string and then store it as is. Yeah, and then so here are some advantages of storing data as JSON. So obviously, firstly, we can support arbitrarily nested object, and then the schema can be flexible. Users don't need to specify the internal structure of the JSON object, and also because of them, there's no need to extract the fields. We can store all the JSON blobs as is. And then because of that, there's no need to actual process and then denormalize, flatten the data. Also, we don't need to join at query time. So let's take a look at the pipeline with JSON support. Basically, we can remove the ETL from this pipeline and then achieve something very simple. We can remove all these extra services and achieve some plug and play experience. Basically, we can directly plug this meetup. We can directly ingest from this meetup JSON topic and then create an RSVP table in Pinot and directly query. So let's take a look at the configs we need in order to ingest JSON data. So actually, it's quite straightforward. So in the schema, we simply put these 4 fields as JSON data type. And then in the table config, we can use the transform configs within the ingestion config to flatten the JSON object into the JSON string using transform function JSON format. So note that for the group JSON, I need to escape group because group is a preserved key in SQL. So then let's go back to the initial question. How do I solve these questions with JSON support? So here I want to introduce the JSON extract scalar function, which can help solving all these questions. So first one, I want to find all the online events. So basically, I want to select the event JSON from meetup RSVP table, and then this JSON extract scalar function is able to extract the venue name from the venue JSON. And then after extracting the value, we can compare it with the venue name we're interested in, the online event. So this query will give us all the events that basically that has venue name within venue JSON as online event. So for the second question, we want to find the name of the events from groups in Mountain View. So again, we can use JSON extract scalar to solve this problem. So the second part within the where clause is very similar to the first query. We can also use JSON extract scalar within the selection clause. And then basically it can extract the event name from the event JSON. Because for this query, we are only interested in the name of the event instead of returning the whole JSON blob. So here's the interesting query. How can we find the URL of the events about open source project? So yeah, so to learn about all the open source projects, we need to know the group topics, which is a nested array within the group JSON field. So here we can see there's something new in the JSON extract scalar function within the where clause. So the group topics is an array field. So we need to use array access in order to read into the array. So here I use a wildcard because I don't care the actual array index of the topic name. So any topic name that is open source within group topics is a matching. But for example, we can easily extend this to like something from the events that has the top topic as open source. So basically here we change the wildcards to index 0. Then it will only match the event with the first topic as open source. Okay, so now let's take a look at the semantic. The syntax of the JSON extract scalar function. So JSON extract scalar function takes 3 or 4 arguments. The first one is a JSON column. Second one is a JSON path expression. Third one is the result type, and then the fourth one is optional as default value. So default value will be used when the function cannot parse the JSON parse. Read the JSON path properly from the JSON value. So let's take a look at some examples. So first one is read the venue ID from the venue JSON. So I want to read venue ID as int, and then if the read failed, I want to return -1. Second one, I want to know the event name from the event JSON, and I want to read it as string. The third one, so basically I want to read all the topic names from the group topics. So the result will be stored as a string array. So this string array will map to the multi-value column in Pinot. Okay, so then let's take a look at what is this JSON path expression. So JSON path expression is actually a standard way of extracting fields from JSON, and then it supports 2 different way of notations. One is the dot notation, which is the one we take in the example, and then it also supports a bracket notation, as shown here. And then here are some most commonly used operators. So for example, in the dot notation, we use the $sign as a root, and then we use star as a wildcard, dot name, so to access the object field, and then the bracket to access the actual array index. There are other operators, but yeah, so they're not used yet, so I'll just skip them for now. So now we have seen how we store the JSON blob using fixed schema and JSON blobs. So what's the pros and cons of these approaches? So basically, as we can say, storing as JSON blobs has much simplified architecture, and then it's much easier to query. But the only cons for storing JSON blobs is it's very expensive to query. So in order to filter on some JSON field, we need to scan and parse JSON row by row and also read JSON paths from them. So for a large table, this can easily take seconds. So next, I'll talk about how to solve this expensive query problem. So I want to introduce JSON index. So what is JSON index? In short word, JSON index is just an inverted index that applies to the nested objects. And it can be used to accelerate the filtering on the nested field values. So to configure JSON index, actually is quite straightforward. In your table index config, within your table config, simply put the columns you want to add JSON index to. So in our example, I want to add JSON index to all these 4 fields. And then I'll first show some performance comparison between JSON index with or without JSON index. So in our performance comparison, I have 10 million records, single segment with person's data, and then I want to find the records with person's name Adam. So the first query is using the JSON extract scalar function, which does not have a JSON index. And then it is slow, it takes 11 seconds. But because there's only a single segment, so basically it uses single CPU core. So the second one, I'll explain this query later, but then it uses JSON index and then it only takes 10 milliseconds. So it's super fast. Okay, now, so these two queries look similar, but the function is different and then the syntax is slightly different. So let's take a look at the JSON match. So JSON match is modeled as a predicate. So when we want to use a JSON index, we should use this predicate to read values from the JSON. So again, let's take a look at all these three queries and how we can solve them with JSON match using the JSON index. So this is the one we showed before using JSON extract scalar. So the first query won't utilize the JSON index. But to change it to JSON match predicate, we simply put the JSON path along with the predicate as the second argument in the JSON match, and then it will automatically use the JSON index to solve the query. Similarly, for the second request, so as we can see, in the JSON match, the first argument is the JSON field and JSON column name, and the second one is a filter predicate, the filter expression. So we want to know the records that has group city equals to Mountain View. For the third one, the open source project. So again, it's quite similar. So it supports the JSON path expression, and then we can match any topic name to open source. So let's add the fourth one. So what if I want to find all the events about open source project, and the event should be from groups in Mountain View? So if we use JSON extract scalar, basically we want to construct two expressions and then join them with AND. So similarly, in JSON match, actually we can push down this AND into the filter expression. So in JSON match, the second argument becomes any group topic name equals open source and group city equals Mountain View. So now let's take a look at the syntax of JSON match. So JSON match only takes two arguments. First one is a JSON column, and second one is the filter expression. So filter expression is always stored as a literal, so we need to put single quotes over it. And then filter expression consists of three parts: the JSON path expression, the predicate, and the literal. So let's see some examples. So here you can say venue JSON is a JSON column, and then venue name equals online event is the filter expression. So here we want to know the group with the first group topic URL key to big data. And again, we need to escape the single code with two of them. Third one is the third question we're asking about the open source project. So basically, it matches any topic name of open source. Okay, so let's take a look at what is supported in the JSON match. So currently, it doesn't support all the JSON path expressions because it is an inverted index. So it only supports exact match as of now. So right now, it only supports dot notation. It doesn't support bracket notation yet. And then it supports dot noted child. For example, the $ dot value name. And then it also supports array index and wildcard in array index. So basically, this should cover most of the common use cases that we can use within a filter. Then also for the predicate, for the same reason, because it's an inverted index, right now we only support exact match. So these predicates are supported. You can use equal, not equal, in, not in. It's not null, it's null, and then we can join them arbitrarily with and, on, or. So actually, there are not a lot of predicates that does not perform exact match. So currently, these predicates are not supported, the range, the reg expression like, and then the text match. So here are some future work we want to add. So as we can see, right now, we still need to explicitly put JSON extract scalar and JSON match in order to query a JSON column. So we want to simplify the syntax and then potentially simplify this query into something like just dot notation. Then it will become super easy to query. Thanks. So this all about my talk. So feel free to try out the JSON index with or quick start script. So we have a batch ingestion quick start with the GitHub events data, and then a stream quick start JSON index with meetup RSVP data. And I want to point out that the JSON data type and the new JSON match syntax, which uses the JSON path expression added recently, and then it will be available in the next release. Please refer to the Pinot documentation for the old JSON match syntax in release 0.7.1. Thanks.
Jackie, awesome. Thank you so much. If anybody has any questions, please ask them now. We can take a couple questions before we move to Sid's presentation. And also, if you guys have any thoughts or ideas or suggestions or whatever that you want to send over to Jackie, you can reach out to him on Slack, on the Pinot Slack. His username is probably at Jackie something, I don't know.
Yeah, just search for Jackie and then you should be able to find me.
yeah, you should be able to find him. He's very active there too. Okay, cool. So we can give people a minute just to see if anybody has any questions, and then, if they don't, because they might have questions that are offline too, they could also ask in the Slack channel if we miss it live. The links are in the description for the YouTube. Thank you, Allison. Okay, great. So, Jackie, thank you so much for taking the time and putting all this together and, contributing to the Pinot project as much as you have and making it the fastest online analytics platform on the market. That's awesome.
Yeah. Thanks, Karen, for organizing this.
Well, we have a lot of presentations coming up from Jackie. He's basically presenting something almost every week for the next 3 months. So, it's going to be a lot of fun.
Yeah,
Um,
yeah, I'll do some deep dive into Pinot. Like, if you are interested, then please come and join.
yeah. No, that's awesome. And we're going to post them all on YouTube too. We're going to try to like nicely organize them to make sure that people can find the content well. And also, if you have any like suggestions or thoughts about content that you would like to see, please ping me and let me know. That's the best way that I can make sure that we bring content to you guys that's actually going to be valuable for everyone. So any suggestions or thoughts are not only welcome, but they're actually requested. So please share your thoughts and suggestions. All right, cool, Jackie. Thank you so much. And I'm going to bring in Sid in a moment. I'm going to give him a nice introduction too, because he also very much deserves it.
Okay.
All right. Thanks, Jackie. All right. Okay. So our next speaker is Sid Teotia. It's the best last name ever. Sid is a senior software engineer at LinkedIn, and he is a PPMC at Apache Pinot and also a PMC at Apache Arrow. So just a little bit of background. Sid works at LinkedIn in the Pinot team as part of the systems and infrastructure group. And prior to LinkedIn, he worked at Oracle for 3.5 years in the database kernel group on storage, indexing, and in-memory columnar query processing. Prior to Oracle, Sid worked at Dremio for 2 years as one of the early engineers building out distributed data lake query engine. He also is a PMC member for the Apache Arrow and has previously given talks at multiple conferences and meetups. So Sid, I'm going to bring you in. Thank you. Hey.
Hi, Corinne. Can you guys hear me?
Yes, we can hear you.
Okay, thanks, Corinne, for the introduction.
Yeah. Thanks.
Hello, everyone. Yep, thank you. Hello, everyone. My name is Siddharth, and I'll be giving a talk on support for text index in Apache Pinot. We'll be diving into some of the design implementation details, some background, and some perf numbers, and how and when to use the text index. Okay, so let's start with some background.
Oh, we have to share your screen?
Can you guys see my screen?
Not yet. I have to bring it in. So we have to.
I see.
Once you share it, I'll bring it back, bring it into the session.
Can you see now?
Yes. Okay. I'm jumping off.
All right. Okay.
Thanks, Sid. Great.
Okay, so yeah, I'll just start by setting some background and context that is necessary for understanding text index. So let's say today, how are we going to do an exact match search without any index in Pinot, right? So let's say you have a column first name in your Pinot table and you want to find out all the folks that have their first name as John, right? So now what happens is when we are evaluating this first name equal to John predicate, and we have a data structure in our Pinot segment format called as dictionary, where we store all the unique values in the column. All right. So the size of the dictionary is equal to the cardinality of the column. So we first find John in the dictionary using binary search. The dictionary is a sorted data structure, and you find the dictionary ID. So in this case, the dictionary ID of John happens to be 2, right? And then we scan another data structure, which is called as forward index. The size of the forward index is equal to the number of rows in a Pinot segment. So here what we are doing is just looking at each entry in the forward index and counting the number of records or rows that have the dictionary ID as 2. So each entry in the forward index is a dictionary ID. So that's what we do today to do a full scan search without any index. And this process, what I just explained, is going to be repeated over each segment in your Pinot table. Okay, so now let's say you do have an inverted index on your first name column. So in this case, how does the search operation change? Again, the same thing. You have a dictionary structure, then you have a forward index where each entry is a dictionary ID, and then you have an index structure called as inverted index. Now in this case, as you can see, inverted index is a reverse map from your dictionary IDs to the corresponding bitmap of document ID. So it essentially tells you for each dictionary ID where and all is this dictionary ID present in your segment. So that's where the bitmap of document ID comes useful. So the process is very simple. First, define John in dictionary, right? Using binary search, you get the dictionary ID 2. Then you just look up the inverted index for dictionary ID 2, and you're straight. You get to the bitmap of doc IDs where this dictionary is present, right? So there is no need anymore to scan the entire forward index. So this index approach is similar to like how indexes work in database, right? Like from pointer from a key back to the row ID where that key is present, right? Okay, so now we support another kind of index which is called a sorted index. So let's say the table was actually sorted on your first name column. Again, the process is more or less simpler. The structure of sorted index is slightly different from inverted index. In this case, the mapping is again there from a dictionary ID, but instead of to a bitmap of document IDs, we have a tuple, right? We have a start doc ID and end doc ID, because and the reason why we have that is because the segment is sorted on this column, right? So yeah, just look up the John in dictionary using binary search, then look up the sorted index using the dictionary ID, and straight you get to the start doc ID and end doc ID where value John is present in your segment. Okay, so this is so now that you know what happens when Pinot is executing an exact match search, now let's basically compare the performance of the three ways we looked at, right? So let's take a sample data set of 500 million rows and a filter selectivity of 150 million. By selectivity, it means that how many rows are going to pass the filter, right? Sorry. So as you can see, scan is super slow. For this particular example, it took roughly 18 seconds for this exact match with scan. Inverted index, super fast, 300 milliseconds. And sorted index is faster than inverted index, right? And with sorted index, the benefit, you get locality benefit, right? So it's more CPU cache friendly because you get that locality, right? You don't have to do that. Dereference or access pattern doesn't really change as it changes with the inverted index. So that's why sorted index sometimes tends to be faster than inverted index. And that's, so you see around 190 millisecond latency for this particular query. Okay, so that's pretty much on how exact match works in Pinot and what is the different performance profile with scan and versus index. All right, so now moving on to text search. Now, how will Pinot today do a text search when there is no index, right? So let's say, so what is the key difference between text match and the exact matches? So essentially, user is no longer interested in doing an exact match. User is interested in doing an arbitrary search, right? And a simple example is, let's say user wants to do a prefix search. So instead of looking for all the folks with the first name as John, a user wants to look for all the folks that have the first name prefix as John. So first names like John, Johnson, I don't know, Jonathan, or those things are supposed to be matching, right? And we have this inbuilt function to support these kind of searches, and this is called as regexp-like. So now, okay, how will the regex match happen in this case? Again, we have the same column first name. We have a dictionary equal to the length of the cardinality of the column, and then we have forward index where each entry is a dictionary ID. Step 1, scan the dictionary and get the raw value for each dictionary ID. So key thing to note is that we are not binary searching the dictionary, we are scanning the dictionary, right? And we are looking at each raw value, right? Now, pattern match the raw value with regex and compute the matching dictionary ID set. So we use the standard Java regex pattern and matcher. So you pull out each raw value from the dictionary, do a regex match with the expression that is there in your query. In this case, it is John star, right? And for each matching dictionary ID, just basically keep on building a set of all the matching dictionary IDs, right? So at the end of step 2, you will have one or more dictionary IDs where the first name starts with John, right? So now there are still dictionary IDs. We don't know the row doc IDs, right? So now what we need to do is that just repeat the process of scanning the entire forward index, right? And count the number of records where the dictionary ID is actually part of the matching set that you computed in step 2. So again, so it's basically the scan, right? Like we learned how Pinot does exact match with scan, right? It is similar to here. You scan the dictionary and then you scan the forward index and you do pattern matching with the provided expression. So the main thing to note is that unlike exact matches, which are very efficiently done through inverted index or sorted index, right? Index can't be used to evaluate regex filters, and we have to use scan. That was the story before we added up support for text indexes. All right, so now move on to how text search with index will be done. right? So use cases like for arbitrary text data, that is more like your like blob or clob like data, right, where each column value can be a heterogeneous text, for example, right, like a line in a log file, right? Each line in a log file can have various things, timestamp, URL, right? It can have performance statistics or anything, right? Or it could be basically it is no longer limited to your standard string data, which is like first name, last name, or anything like that, right? And on this such kind of data, typically users want a regex phrase. Regex is basically regular expression search. Phrase is basically combining multiple terms, and you want those terms to match in the exact same order as you specified in your search expression. And then fuzzy is more like an edit distance like search, or like something similar to like spelling correction like search, right? So on such kind of data, users are interested in running these kind of search operations, right? Additionally, users want the ability to compose, basically put together a single complex Boolean search expression, which is consisting of one or more of these different search styles, right? Like you can combine one or more terms, you can combine one or more phrases, and then regexes or fuzzy, right, using and or, and put together a complex search expression, right? And the thing with the existing regexp like inbuilt function is that if you're on a very large volume of data, right, and let's say you do not have additional filters on other columns which are going to prune uh, the search space, right, and then regexp like will pretty much end up scanning the entire table, right? So what we observed is that most queries will time out during execution when filtering large amounts of data. And the requirement that I mentioned in the third bullet point, right? The regexp like is you basically syntax is that you should be familiar with Java regex semantics, right? So now if you were to put together a complex Boolean search expression, right, for terms, phrases, regex, right, it is easily going to get very non-trivial, putting together all those permutations and combinations following the standard Java regex notation. Yeah, you can, I mean, if you're really smart with regex, you can potentially use look back and look ahead with groups, but then again, it is not very user friendly in my opinion. So that's why, with all keeping all of these requirements and use cases in mind, we added support for text indexes for our efficient arbitrary text search in Pinot 0.3 release. Right, so let's quickly look at the performance of the text search with and without index. It's the same data set, 500 million rows. It's very, it's not a highly selective data set. The selectivity is pretty low. So that's why 150 million rows are getting selected. So the text search with scan timed out actually after 8 minutes. And with index, it finished in roughly 2 seconds. I'm going to be talking about more performance numbers and exact query examples, etc., in the coming slides. But this is just to give a brief comparison on text search with and without index. All right, so let's look at how we are going to create text indexes. So Pinot currently uses Apache Lucene to create a text index. Then Apache Lucene is basically an open source library for building full text search like capabilities. It's an open source project. We use columnar format. So just like you store, each column is stored in a columnar format along with its indexes, etc. in Pinot segment format. The text index follows the same protocol, right? So similar to other index and storage structures, text index can be created at a per column level. Sorry about the Slack notification. Then it is the text index generation is part of Pinot segment generation for each row in the table, right? As and when it is being ingested into Pinot, we take the value of the column that you have enabled text indexing on, and we create a document. Document is nothing but it's like an encapsulation over the body of text, right? And the document ID, right? And document is essentially the unit of indexing. And the text index is supported for both offline as well as your real-time and hybrid tables. And it is supported on string columns. One thing I forgot to add is that it is only supported on single value string columns. It is not supported on multi-value string or the bytes column type. All right, so now let's look at one of the design details during for as part of creating text indexes. So Pinot, as I talked about in the initial slides, right, we have a concept of doc ID, which is heavily utilized during query processing. Our entire filter execution engine, right, or projection or anything depends on the us being able to correctly fish out the doc IDs for the matching rows, right? So we decided to store the Pinot doc ID for each row on which we are building an index on inside the Leucine index document. And the rationale for that is this. So Leucine index is essentially composed of multiple subindexes, and each subindex is like a self-contained searchable entity, and it maintains an internal doc ID for each document in the index. So the key thing to note is that the internal document ID that it is maintained in a subindex by Leucine is relative to that subindex, right? And obviously number of subindexes depends on data size, flash frequency, background split merge, a lot of whatever the Leucine secret sauce is there. We have some mechanics in our code to control some aspects of that, and I'll touch upon a few things in the design considerations. But anyway, it's essentially controlled by Leucine. And as I said, right, so if we are going to trust Leucine doc ID, we are going to give wrong results. Why? Because it is relative to each subindex. It is not an absolute range of doc IDs, right? So now, how, in order to associate each document that is added to the Leucine index to the absolute Pinot doc ID, we decided to just add the document ID to the Leucine document. And that's the reason, because we wanted our execution engine to work correctly and to play nice with filter matching and other things in our execution engine. All right. The other part of text creating text index is a text analysis. Plain text, which is whatever user gave us in the column, right, in the input data, right, that is used for index generation. The first step is analyzer, which performs some basic pre-processing steps, right, which is like lower casing so that the searches are done in case insensitive manner, then tokenizing the text into individual or indexable tokens terms, right? So it uses a segmentation algorithm to basically separate your raw text into different words and terms. We currently use standard analyzer. Standard analyzer is basically, it works for very well for English alphanumeric texts and uses Unicode text segmentation algorithm, which is like a general algorithm widely used across the text search landscape in the databases, right? And to break text into multiple tokens. And then this is fully customizable. In fact, Leucine advocates that if you were to just customize it, it is very easy. The interfaces and abstractions are laid out pretty well for us to do whatever however we want to customize the analyzer, right? And let's say you want to add some stop words, let's say you want to handle apostrophes, right? Or let's say you want to handle internationalization for different languages and all those things. All right. So now, as if you're familiar with Pinot, then we have two kind of segments, right? One is the immutable or offline segments, other is mutable or the real-time consuming segments. So text index for offline Pinot segments. Offline Pinot segments are generated in an offline batch Hadoop job. They don't serve queries while they're being created, and so all indexes are immutable. So what the text index writer does, our Leucine, our text index writer, which is actually responsible for building the index, buffers the documents in memory up to a certain configurable threshold of memory, right, and periodically flushes them to on-disk Leucine index directory. And then when the segment creation finishes, right, in your batch job, then the index writer commits the text index and just thus making all the changes visible to the index for subsequent searches on your query execution path. So index is sealed and it is done. It won't change in the future again because the segment is immutable. Then for the real-time Pinot segments, it's a slightly different story. They are generated while consuming data from streaming sources like Kafka, and the key thing is that they are queryable as data is ingested. So that's why this index is mutable, right? So the main requirement over there is that we need to be able to search the text index while a live index writer, right, is in progress with uncommitted changes. It is adding documents, and on one hand it is adding documents, on the other hand you want to search it. So further slides will talk about like how how real-time path is slightly different from the offline path. Okay, so now moving on, now that we have discussed how the text indexes are created, let's discuss how they are queried. So we decided to introduce a new inbuilt function, text match. And the syntax is fairly simple. The first argument is the column name. The column name is the column on which you've enabled text index, and search expression is basically your text search query. And you should use this in the where clause for text search based filtering. Execution engine was enhanced to parse, compile, and execute the text match function. It is parsed as a string literal by Pinot compiler, and the using query parser parses into an expression tree of basically a Boolean standard expression tree. So the key thing to note is, right, like a lot of the fundamental building blocks of Pinot, right, they help when you add a feature like this, right? Like none of that changes. The query parsing did not change. We just added to it, right? Similarly, all of our index, reader, writer, we just added over there, right? So it's fairly the way Pinot is built, right? The way modules are arranged and the code is arranged, it's very easy to wire in a new filter operator or a new reader writer into your query processing code path. Yeah. So that's why minimal changes, right, around these basically areas of Pinot. Okay, and then it is you can use SQL to query the text index. So basically, it's the standard SQL syntax with the addition of the text match function. So let's take an example of, let's say you have a query log file. Let's say the Pinot broker query log file, right, where each line is a query that you ran against a Pinot cluster, and let's say some resume or profile text. So store the data as 2 string columns in a Pinot table, and then you enable text index on each of these columns. So the first query, potential query that you can run is, let's say you want to find the number of group by queries in the log that must have between filter on the time column, right? So you do select count star from my table, where text match and the log text call is the name of the column on which you have enabled text index, and then what follows is your search expression. And you see it's like a Boolean expression, right? So what I'm looking for is a phrase time call between, right, and a phrase group by, right? So it will look for the exact phrase where the time call is followed by between, right, and then group is followed by, and each matching document must have these 2 phrases. Another example, let's say you want to find out the number of candidates that must have skills like machine learning, GPU processing, and let's say one of distributed systems or Apache. So again, select count star from my table, then text match profile text call is the second column on which you enable text index. The first phrase is machine learning, then it's a must have, then you add GPU processing and another must have, but there you have a condition, you are either okay with distributed systems or you're okay with Apache. So then just basically it's the standard way of writing a where clause query in any database, right? Like how you can put together multiple predicates, combining them with and or. So just exact same syntax is applicable here, with the exception that you need to be careful of using the quotes for your to basically tell you scene that this is a phrase. Let's say you want to, then another example, which is not a phrase query. Let's say you want to find the number of candidates that have skills like streams, streaming, real-time stream processing, or something like that, right? So essentially you can do a prefix query, right, which is like falls into the regex query landscape of text search. So essentially we are text match, profile text call, and then your simple prefix query stream star. So these are the few examples on the kind of analysis that you can do using SQL queries with text index. All right. So now let's dig deeper into how the offline text index works, right? So basically you have a data ingestion path. You created an offline segment with 2 indexes, with text indexes on 2 different columns, right? And then you basically put the segment in your segment store. On the right hand side, you see an offline Pinot server that loads the data from your segment store, and it basically maps the entire segment. So text index is created in a subdirectory in the segment directory, and that subdirectory is also memory mapped, right? An instance of text index reader is just created per text index during segment load. So as you can see, we have a filter operator for handling one predicate, text match on first column, text call 1 with that corresponding expression. Another filter operator on another column, with the corresponding expression. And they just use the text index reader, which executes the search expression. That is step one. Step two is basically for step one is you get the instance of the reader. Step two is basically execute the search, compute the bitmap of matching doc IDs, and then whatever Pinot does today just follows easily, right? So it's an AND query, so you're just gonna intersect the two bitmaps of matching doc IDs to finally compute the set of matching doc IDs where both the text match clauses are satisfied. For real-time segments, things are slightly different. As I mentioned earlier, we need to search the index while documents are being added. Lucene supports NRT, which is the near real-time search by opening a reader from a live writer to search the uncommitted index data. And it is a snapshot reader, which means even though you have opened it from the writer, right, live writer, it is a snapshot. So it will work as of that point of time where you open the snapshot. So you need to refresh it. And a real-time index reader, and this is true for all index readers in Pinot, not just text, right? They are real-time index readers. They also act as writer. So they are adding documents to the index as part of real-time segment consumption, and they are also being used by the Pinot query threads. Okay, so now let's see what is happening. So let's say you have one segment, which is the real-time consuming segment, and when the segment instance is created, right, we add it to a global circular queue where there is each entry is for a particular real-time text index. And so the segment is created, and then the consumption will begin, right? So now let's say you have like a query, right? And you're going to execute the text search filter operators, which will work which will be invoked by a query thread. Then there might be another query thread on another segment, right? So what is happening is that there is a background refresh thread that manages this global queue. Its job is basically this: it pulls a real-time segment from the queue for each text index reader on the segment. And on any segment, there will be as many text indexes as the number of columns on which you have enabled the index. It basically refreshes the index searcher, right? That is used by the query threads to search the index, and then atomically swaps the searcher reference inside the index reader with the refreshed searcher. And the key thing to note is the way the concurrency is being managed between the query threads that are searching the consuming segment, or that are reading the consuming segment for text index search, as in the background thread that can come in any time and then just refresh them, is basically reference counting. So these two folks, the blue boxes, are holding a reference to the searcher, right? And once they acquire it, the searcher will hold, right? Background thread might come up anytime and can actually refresh the searcher. So the next time they acquire the reference, they might get a refreshed one because this guy would have come in between and would have refreshed it. So it's a standard protocol that these three guys are communicating with each other using reference counting, so that the search code path doesn't really end up dereferencing a searcher that has been closed, right, or no longer valid. Yeah. So that is the key thing that is different between the real-time segments as well as offline segments for text index. All right. So the single background thread wakes up after a configurable threshold, pulls the reader and from the global queue and refreshes it. Now, how often should this happen? It's typically controlled by your requirements. So if it is too low, we refresh too often, but the search queries will get to see the new rows quickly. So the downside is like a lot of IOs, right? Small IOs. But if it's high, we flush less often, but this increases the lag between the time a row was indexed, right, on the consuming thread, right? But the time it actually appears in our search results. Why? Because it didn't get refreshed, right? So should be tuned on a per use cases basis depending on the requirements. The current threshold is pretty low. The default is 10 milliseconds. We can configure it, and we have a couple of users in open source who are actually using text index purely on a real-time table. We haven't had any concerns yet. Like for one of the performance numbers is that the average latency we are seeing is around 20 millisecond for a roughly 3 terabyte data volume. It's a low QPS real-time use case. But we are going to get feedback from such users that are primarily focused on using real-time text search, right, and then improve upon this refresh semantics. The few design considerations and optimizations. We used a collector callback to bypass the default search path in Lucene. Why? Because the default search code path results in significant heap overhead. When we started this initiative, we did a lot of experimentation and messing around with Lucene, measuring the CPU, I/O, and heap overhead, and it was non-trivial because Lucene does a lot of additional stuff that we don't want: scoring, ranking, etc., and using a priority queue to return top hits. We don't want any of that, so we just provide a simple callback to Lucene. Every time there is a matching document ID, they invoke our callback, and we put the document ID in a bitmap. And that bitmap plays a document ID plays nicely with our rest of the execution engine and the filter processing. Then typically it is common that the this text, right, like huge text, they have stop words like a, and the, right, stop words, which means they will never be searched in the queries, right, and but they have the potential to increase the size of your index and can also hurt your query performance. So the analyzer actually can prune the stop words to reduce the index size and improve performance. So we customize the analyzer to just basically add a set of stop words, right? So they are just pruned from the index during the index generation itself. Then there is a Lucene query result cache. The performance is actually pretty good with it if you have repeatable queries, and we have seen good improvements if, let's say, the text search expressions are repeatable. But it increases the heap overhead significantly, actually, because it is like it's an on heap data structure. So that's why we decide you can still configure it to enable the cache on a per column basis, but you should consult with the Pinot dev in the open source channel before doing that. That's why we disabled it by default. The other thing that there was a key optimization, right? Like that we saw that CPU bottleneck with increasing QPS, so latency was not able to scale well as the QPS was going up. So remember I talked about how the Pinot doc ID is stored in every Lucene document, and that actually results in a 2-pass query execution. You search, the operation gets a matching doc ID, Lucene doc ID, and for every Lucene doc ID, we fetch the entire document from Lucene, and from the document we retrieve the Pinot doc ID. So this operation of fetching the entire document from Lucene and then retrieving the doc ID was a CPU hogger and became a major bottleneck for our throughput testing. So what we did is that we iterated the text index once at the load time, right? When the Pinot server loads the segment or memory maps it, right? We iterate over the index. We build this mapping, which is Lucene doc ID to Pinot doc ID, and store it in a memory mapped file. Then the query execution path doesn't have to fetch the document anymore, right? The collector can simply get the Lucene doc ID, right, and it can look up this mapping to get the corresponding Pinot doc ID and build up and just keep on building a bitmap. So this improved the performance significantly. And that's, yeah, as I said, the mapping file is used during query execution for conversion of doc ID. So before, like, blue bar represents without this optimization, right? Like, as you see, as the QPS was going up, and QPS is not that high, it's like only from 1 to 100, right? But the latency was just increasing, right, like rapidly, went up to like 45 milliseconds here. But with this optimization, the latency pretty much remained the same, at least until 100 QPS, right? It was under the order of like 100 milliseconds or so as the QPS was going up. So this optimization was very, very critical. Then we have some potential improvements that I'd like to talk about. One is that the doc ID translation optimization for querying text index. We need to do that for real-time segments, and that is one of the things that I've been working on with a couple of users in the open source who are using text search on real time to get some feedback on performance and then accordingly do this. And then we, as I said, the background refresh thread, that is actually having a global queue. I think we may want to consider having a bit of fine grain scope over there. Basically, either do it on a per table or a per index basis. Haven't seen any performance issues yet, but yeah, something to do. The other thing is positional inverted index. This is interesting, right? Like, if, let's say, Pinot, as I talked about, we have a native inverted index, we have a sorted index, but our inverted index is like a mapping from your dictionary ID to where that dictionary ID is located, dictionary ID to a set of doc IDs, right? But we don't track position of the term, right? So exact term, if we are actually going to build a positional inverted index where we can track positions, then the term and phrase queries can be executed inside Pinot only the regex queries can be delegated to Lucene index. That's one option. And I did a prototype, essentially a hack, right? But just by uh, putting the positions in a file, just an hour's job, and then see, just not delegating that query to the Lucene index and see what we get out of. And the speed up is significant, and that is expected. So this can be a really good optimization where we only use the text index by Lucene for maybe, let's say, regex queries or fuzzy queries, right? And term and phrase matches are done completely natively inside Pinot. Now, the most important question, right? Like, do you need text index? So if only exact matches or terms are needed, right? Like exact matches, like as I talked about my initial slides, first name equal to John, right? So John is like an exact term. Then Pinot's native inverted or sorted index are they are the right solution. In fact, we had done performance testing on this as part of this effort as well. And the exact matches, these indexes, our native indexes, can do exact matches using equal to or in or not equal to not in filter operators on term to 5x faster. Right, so exact matches you should use Pinot's native index. However, like let's say you are more interested in doing phrase searches, which is like the multiple terms in the same order, or like arbitrary or regex searches, right, or fuzzy searches, or any combination of these, as I shown in the examples, right, like by combining these into a Boolean expression, right, then you should consider using text index to get the desired functionality as well as performance benefits. Yeah, that's pretty much. There is a blog post that we wrote last year that goes into a lot of more sorry, design and implementation details and some additional performance numbers and trade-offs that I did not mention in this presentation. Then yeah, there's a link for user docs for text search, pretty detailed. You can read it to learn more about text search query syntax and how do you go about configuring it for your table. We have a blog post coming out this week, today or tomorrow actually, on how we are using text search in production at LinkedIn for one of our critical use cases. So yeah, we'll share that with the community either later today or tomorrow. That's pretty much. Then we have links to our Apache, Pinot, Slack, GitHub. We'll join the community. Yep.
So this is amazing. Thank you so much. And thank you so much for all your hard work contributing to these projects. This is a big deal. If you forward me over these links, I can actually put them directly in the YouTube description to make sure that people can access them even, now and after the fact.
Sure. Yeah.
Great. So we can give people a couple minutes for questions, just see if they have any questions. I feel like it's been kind of like a silent group today, which is kind of strange. There was someone who had a question about the hardware requirement for your company's production environment.
Is it for me, Jackie, or?
I don't know. They asked the question. Mayank asked if you could provide more context. But Jackie said commodity hardware is enough, and we recommend at least 4 GB memory. Pinot is horizontally scalable and highly available. So that's what he said.
Right.
If there's anything you want to add to that.
I think that's pretty much that I would also say. And obviously, like whatever the setup that we have, that we are using in production, right? That we are going to talk about in detail in the blog post that is coming out today or tomorrow, and how we actually scale this feature to handle our production requirement.
It's awesome.
Yeah.
Here, I'll bring Jackie back in too. Oh, Ken has a question. With no positional, I don't know if this is the question. With no positional information, what's the comparison between just using Lucene to tokenize, normalize, and storing that as a multi-value field versus a full text index?
Yeah. So so we can still tokenize using Lucene and then store it as a multi-value column, right? But the multi-value column search is position agnostic, right? So it's like if you're saying this is a text index, right, and you want to search and you store it as a multi-value column where you have like 4 values in that row. This is a text index, 5 values, right? Then the search will match anything. It will match like index text, or it can match like text index. It is still position agnostic. So the position information is missing to support phrase searches like the way Lucene is doing to get the same functionality. So we can still like one of the key ingredients to building the multi-value positional inverted index can actually be leveraging the multi-value column. But again, the position information has to be there.
Cool. Hopefully that answered your question, Ken. Oh, he said, right, but do you support phrase queries now?
We support phrase queries today using the text index. If you are using any native Pinot native inverted index, right, you can do any search, right? And but it is going to be an exact match using that, right? So you will have to search the entire phrase as is. So if you stored a large document that has like hundreds of terms, right, and you're looking for a particular phrase in that, which is comprising of a subset of 3 terms in that same order, Pinot's native inverted index today won't be able to do that. Using text index can do. And that's where the improvement of positional inverted index comes into the picture.
Nice. Awesome. Does anybody else have any other questions? This is your time to ask. Of course, ask on the Slack. Okay, is it possible to create a JSON plus text index? Example, one of the attributes of JSON is text.
Yeah, I think we have had this requirement. It showed up in OSS in the past, and I think, yeah, so like we should consider that it's possible. Today I don't think so we support it.
Yeah, so currently the workaround would be so we have recently added a feature to extract certain field using transform. So basically what you can do is, if you know the path of the attribute in the JSON, you can extract that field into a string column. Then you can apply text syntax on top of it. Yeah, but yeah, directly apply JSON plus text syntax into the JSON blob is not supported yet.
Any other questions or thoughts? This is actually really good. I think it's also helpful for like what people are looking for and what they're thinking about too. So we can give people another minute just to write out their questions if they have any. But of course, as you guys all know, if you should know, if you don't know, then it's okay too. But if you do have any other additional questions and you didn't catch Jackie and Sid in the live stream here, you can definitely ask in the Pinot Slack, and they're there. So you can, ask them directly. You can ask in the, one of the other channels like troubleshooting or general, depending on what it is that you're asking about. So cool. So sounds good. Thank you guys so much for doing this. I really, really appreciate it.
So thanks, Karin, for setting this up. Really appreciate it.
Yeah, this is awesome. So we're going to post it on YouTube. We're going to segment it so people can, find it easily and be able to like get through it. And if you guys have any other like sources that you want me to link to, we can like connect them back and forth. So like I can put any links into the YouTube description here too.
Sure.
Cool. Thomas asked if there's any official support available for Pinot.
Official?
Official what? Can you elaborate this question? I don't.
Just Thomas, if you could elaborate on the question of what you're thinking about. Mayank just asked for clarity. You mean like a hosted service? And then Thomas asked commercial support, like any kind of commercial support. So yes, Mayank is always in there just answering all the questions. We've been in other meetups where Mayank answered all the questions that like normally when the speakers come in, they're like all the questions have been answered already.
Yeah, basically that's what we do here at StarTree.
Right. So yeah, StarTree was created by some of the original creators of Apache Pinot to offer it as like a hosted cloud service. So you can like look at it at startree.ai. And actually, I'm going to use this as a plug for another event that we have coming up. which I'm excited about. It's it's kind of like our Star Tree launch event, but it's really covers discussions about real-time analytics and also user-facing analytics in the space. And there's like discussions and presentations and things like that. So we're pretty excited about it. Yeah, this is a really cool project. The Pinot project is like, I'm excited to be part of it. It's awesome that so many people have contributed to such a massive, amazing open source product, you know? And if anybody here, any of the viewers, if you guys, like, again, if you guys have any suggestions or thoughts about anything that you'd like to see in terms of content that you think is missing or you think you'd like to see more of, please let me know, because that is the way that we can actually make it happen and it'll be helpful for other users. So yes. Okay, cool. So I think we can wrap it up. We went over a little bit, 20 minutes, but that's good. So I think it was a lot of really good content. Thank you guys so much, Sid and Jackie.
Thanks, Kareem. Thanks, everyone.
Thanks, Kareem. Yeah.
All right. Bye. See you guys next week.
Yeah. See you next week.
See you next week. We'll be presenting again. All right. Bye-bye.
Bye.